But for now, let's welcome the rest of the online meeting group here. And we've got some fun parts of this coming up here, because first we'll have electrical and then plumbing and mechanical. So of the electrical illustrations, this one gives us what the NEC requirements are for clearances, overhead conductor clearances, for basically for service drops. They're almost the same for feeders. And the problem that we often find with this is that it's not just really an NEC issue, that they're also governed by the utility provider, and they have their own sets of rules. For instance, in our state, we have a separate complete set of ordinances from the Public Utilities Commission on what these heights have to be. It's fairly consistent with what the NEC says, but not always exactly the same. But we find this as a good guideline nonetheless for certain things that, again, that affect safety and that are common sense in a way. Especially this one over here on the left about the distance to an openable window. We don't want somebody being able to reach outside their window and use the electrical service wires as a clothesline. So here's an example from a house that, gosh, I think I probably looked at this 40 years ago. And you can see that what happened here is someone built an addition on the back, and they built it right underneath the existing service drop. And so what you have is something that is a potential hazard to people working on that roof, or even a firefighter walking across it, whatever. So it's just an example of something where I think I would use the illustration and point out that that's not allowed to be so low over that roof there. Basically, the rule for clearance in front of a piece of electrical equipment that might require servicing is, can I put a refrigerator in that space? Okay, that is a space that's 30 inches wide and 3 feet deep. And so this box does not necessarily have to be centered in front of that panel, but it has to have those dimensions. It has to have at least 30 inches of width and 3 feet of depth. And for the last 30 years, the codes have also said that that working space extends all the way to the floor. Didn't used to. It used to be that you could have some permanent piece of equipment like a clothes washer even in front of it, but not anymore. There's a requirement for, and a lot of confusion too about how to do this right, for feeders that supply separate detached buildings. And today we basically always provide a 4-conductor feeder and treat this like a sub-panel, which is to say that we don't bond the neutral in that we have a separate equipment ground, we have a separate neutral. But the difference is that whenever it's more than one circuit in this separate structure, it requires its own grounding electrode system. And that grounding electrode system is there for the same reasons that we have a grounding electrode system at our house, which is that it's primarily to prevent voltage gradients from affecting our systems. It's to protect us from lightning. Okay, it has nothing to do with helping our circuit breakers to protect us when there is too much current going through the circuit. That is not the purpose of having a connection to the earth. The circuit breakers don't care about the small amount of currents that could actually be traveling through the earth compared to the large amount of current that could be carried on an equipment ground. So this is often very it's caused a lot of confusion to people. So what happens is that the people will think, well, gee, all I have to do is just connect to a ground rod at my second building, and I don't need to have the equipment grounding conductor in the feeder. Well, yes, you do. And you keep your neutral free of it. So this is an
I see
example.
this, I would say I see this wrong a lot. I just did a, matter of fact, this report was a $5 million new construction where the main service came into the garage, and the main house had 2 sub panels, neither of which had any kind of apparent separate grounding system. There is one question here from the great state of Florida. Mr. Larry Serra wants to know if sub-panel clearances take into consideration in a garage where the car would be parked.
There isn't anything, as far as I know, in terms of the only concern would be if the vehicle could hit the sub panel, in which case it would require some kind of a barrier. But no, you can move the car. You can move anything that you've set in front of it. It's only things that are permanently a part of the structure, such as, say, a workbench in front of the panel. That would be restricting the clear space to the floor. Okay. This illustration is showing all of the different materials that are used as part of a grounding electrode system. We've got our ground ring shown, building steel, the concrete encased electrodes. These are very common in the West Coast, and metal underground water piping, and the if all else fails driven rods. So the basic idea here is that you use everything that's available to you as a means of connecting your electrical service to the earth, and that you can use the water piping as a means of bonding those things, but only within this first few feet of where it enters into the building, because after that, we don't necessarily trust it to be electrically continuous. And this illustration also is giving us some of the minimum sizes based on the size of the service conductors. By the way, this table here in the code, this is one of my pet peeves. It showed up in the 1934 NEC. There's no one remembers where this came from or why, but the basic idea is that the larger your service conductors are, the larger your grounding electrode conductor has to be, on the theory that you're going to have a greater magnitude of current that you might need to have essentially for lightning protection. But there aren't any studies on this that actually justify it. And if you don't have any of these other things, you don't have building steel, you don't have a concrete encased electrode, you don't already have a ground ring, you don't have metal underground water piping, but you have a 600 amp service, all you need is a ground rod, and all the conductor to it ever has to be is a number 6. It never has to be any larger than a number 6. So there's a lot of contradictions to this. It's one of those, I shouldn't go into it too much, but it's one of those confounding things in the electrical code.
Questions?
Yes.
First one is, what is the value of citing building codes, even by implication, for the purpose of helping a buyer complete a purchase of a home in a jurisdiction that has not adopted the referenced building code, when the modifications could be recommended without reference to building code?
Skip, that's a report writing question. How do you deal with that?
Sorry, I was muted. I saw that and I thought that's probably for me. I choose to sometimes put code references in my reports. I do not recommend other people do it, simply because I know what the codes are adopted here and a lot of the local stuff. And it's not for the buyer. I do it so that when the contractor whines and says, well, that's the way we do it here, I just point to the number and say, look it up and have a nice day. And it for me, it's dropped the number of stupid calls from contractors radically. I never put the citation in, I just put the number, and because they're supposed to, in California, have a copy. So anyway, that's my personal twist on it, not suggesting you guys do it at all.
Thank you for that. And I would think also there's safety issues involved. The
Mhm.
other question is, when there is more than one circuit and a GES is required for the garage subpanel, does the ground screw stay installed or does it get removed? I think probably talking about the panel bond screw.
Yes, they are. And the answer is what's in the feeder. If the feeder from the other building, from the building that's supplying it, contains both a neutral and an equipment ground, we keep them separate. We want all of the current coming back on that neutral. We don't want it traveling on the equipment ground. If in older buildings, and they allowed this up until the 2008 code, if there was no parallel path, conductive path between these two buildings, you could use the neutral as the equipment grounding conductor. You could leave out that fourth wire. And you could, in that case, you did connect the neutral and ground in the separate building subpanel. But you were not allowed to do that if there was any other parallel path between them. And an example of a parallel path could be something as simple as a landline telephone, because it's going to be grounded in both buildings. And if you did that, you would end up with current on your telephone wires, which they're not rated to carry. Okay, or if you had, say, water piping between the buildings, you could have a situation where there was current on it, and when the plumber comes out and cuts the water pipe and grabs a hold of the two sides of it, now the current's going through him. So since 2008, they've made it clear for construction after that you must supply that the 4-wire feeder, and in those cases, you always pull out that bond screw out of the subpanel in that separate building. All right. There's a few other detail illustrations in here about grounding electrodes and their connections. One of the things that we see is, let me go back to this one. This is showing that a conductor that's a number 6, which is only one size larger than the minimum you could ever have, which is number 8, that a number 6 conductor can travel on the surface of a building and be considered to not require any additional protection. But sometimes you will find that, especially if the rod isn't driven in all the way, if it is something that somebody could step on that and break it, I would point that out. But what happens also is that a lot of times you'll see that the conductor is protected by a metal conduit. And if it is a metal conduit, then that conduit actually, in the event of there being current carried on that conductor, as a result of the induction of that current into the conduit will carry most of the current, not the wire. And therefore, the conduit has to be bonded at both ends, bonded at the panel and bonded at the grounding electrode connection. And so here's an example of one that is not bonded. And so what could happen is that if there was a high current imposed on this, it would be induced onto this metal conduit, and where that metal conduit ended here, it would, the inductive reactance of it would cause all of that current to be concentrated right in the center and could even fry that wire. In the Loma Prieta earthquake, we saw a main bonding jumper in the service equipment for the county building in Alameda County. That was a 750 kc mil conductor that burned through from exactly this condition, because it was a massive immediate fault when that happened from the air conditioning flying off the roof.
Douglas?
Yes.
There was one person that said, could you repeat the discussion we had in the previous group about code check illustrations and how that's a name and not an implication of code?
Yes. Oh, let me finish this one here first, because we've got an example of it done right. Okay. This is what you should see. That if it's got a metal conduit, the metal conduit bonded to that, not like this. But back to that other question. The code check illustrations are basically, I said this before, that what we're trying to do is show what code requirements are, and the code requirements by themselves are fairly dry things, but how those codes come about is as a result of experience that has been usually learned the hard way, that there's safety questions behind all of these things, and that we feel very passionately about some of these things ourselves. So when we're writing code check, we're trying to think to ourselves, what can we put in here that will really drive home a point that makes a difference to people? So the current set of code check illustrations, there's a little over 300 of them. We're only talking tonight about less than a fourth of those because of the amount of time that we have. But what we're trying to do is just basically help show the ones that have to do with safety and performance of a building that that we think are the more critical ones. So I think that as we get through this, as we continue on here, we're going to see a lot more examples that are familiar to everybody that's a home inspector.
The concern I think they had was was when we discussed the use of the word code check on the illustrations. Now that's the name of the product. It's not
right. Code check is the words are trademark of the Taunton Press, and the company Code Check is a company that we own, and that and it's the name of a product. It doesn't mean when you put this in there in your report that you're implying that you're the authority having jurisdiction to say what is to code. It's simply the reference that this came from.
If we didn't put the word code check on there and the copyright symbol, we'd actually lose our own copyright.
That's true. So back to grounding electrodes, you can see that PVC Schedule 80 is a much easier way to protect these wires because you don't have to worry about the bonding, and it's actually stronger than EMT. Let's continue on. I hope that you guys are seeing these intersystem bonding terminations. First off, in general, and I'm curious about this, maybe Jim, you could answer for everyone for me. Do you usually find in your part of the country that the service disconnect for the building is inside the building, or is it on the outside?
Outside.
It's on the outside. Oh, okay.
No, sorry, service disconnect. Meters outside, disconnects at the panel.
Disconnects at the panel, inside.
Yes.
Right. So when you guys adopt the 2020 National Electrical Code, you're going to have a real issue there, because it requires that there be an emergency disconnect on the outside, which is essentially the service equipment typically, although it could be a shunt trip or something else. But what also happens is that service equipment where that disconnect is the furthest downstream point where you can have your grounding electrode conductor originating. That it could originate from your meter. It could originate actually from your service drop. It could originate, I think Larry Serro is on the call here. He could probably tell us how they do it in Florida, but I'll bet that in Florida, Larry, most of the time, don't you see it that it's in that the grounding electrode conductor originates from the meter?
No, I'd say 90% of the time it originates from the main panel.
Really? Okay. So you've got this thing originating from the main panel, the service equipment, we'll call it. Okay. Gosh, wipe my mouth out with soap. I used the words main panel. Ugh. Anyway, that grounding electrode conductor connecting to the earth is basically connecting to something that we're going to call 0 volts. But is it actually 0 volts? It isn't really. In fact, we had a guy who lived out in the woods in Mendocino County who found a way by putting ground rods into the earth of getting enough voltage potential difference between them to operate the light bulbs in his tent. This was a person who lived out in the woods. What can I say? So it's not really 0 volts, okay? The time that it's especially not 0 volts is during a lightning storm, in which case it could be that there are very, very large voltage differences in the earth. In fact, if there's a nearby lightning strike, it might be that it could be from one side of a house to another in the earth. It could be hundreds of thousands of volts different. And so what happens is that suppose your cable TV provider comes out and they drive their own ground rod. Well, they've got this ground rod and this little tiny ground wire that goes with their cable, and it goes into the back of your television. And a ½ inch away, you have the electrical outlet for the wire for the power for your television, and its neutral wire connects to this ground rod ultimately. So what happens is you're taking 2 points in the earth that are far away from each other, and you're bringing them close together at the back of your television. And if these things that are far away from each other and that have maybe 100,000 volts difference between them are there, and you suddenly see that in a lightning storm, your television is no longer functional, or other electrical appliances aren't functional. And the result is then that the cable TV guy's own ground rod basically killed your TV. So what the code requires is instead that you take that cable TV and your telephone, everything else, and have an intersystem bonding terminal that ties them all together. And that by tying them all together, that what happens is that there aren't any voltage gradients between those systems. You could still put a ground rod in for the cable TV guy, but he has to have this intersystem bonding termination. And this is a good idea. It's been in the code now for a little over, I guess it's 22 years now. So here's an example of what one might look like on the outside of a building. Take the cover off of it. It looks like that. And you've got to have at least 3 other empty ports to putting in cable TV, maybe satellite dish, maybe telephone. They used to have telephones, used to be with wires. When we first did this illustration, we also showed connecting the CSST bond to it, and the response was immediate from the people who on code making panel 5 to say, no, it's not for the CSST, it's for these other electrical systems. So keep your CSST off of this. So they also make this nice protective conduit fitting. We've got our grounding electrode conductor inside there, and then 6 little terminals for it. It's a nice way to do it, I think. I like this.
Question,
Yes.
do the surge protectors that attach to a 240 volt breaker really work?
Yes. The 2020 NEC requires, I'm going to make the screen go blank for a second here. So don't worry, this is not a technical glitch. Wait, it didn't go blank. Okay, never mind, it is a technical glitch. In the 2020 NEC, there is a requirement that every service have surge protection. And the surge protection device can be ahead of the main breaker, or it can be at the panel that has the main breaker. It can't be more than 30 feet downstream from it. And that it has to protect, therefore, the whole electrical system. Now, a surge protective device, as compared to a surge arrestor, is something that's intended to handle a voltage up to 1,000 volts of surge. But what you also have in these devices is they're built to a standard that can interrupt a very high current and a high frequency current that is within those voltage ranges. You would actually have that kind of high frequency current and high current from a nearby lightning strike. So what it's doing is it's protecting your whole electrical system from that kind of damage. It's not just the overvoltage surge that might occur from a glitch in your power company's supply. It's also providing a great deal more protection from lightning. It's not going to protect you from a direct lightning strike on your house, but it's going to protect you from indirect ones. So those are very important and required for every electrical service in a 1 and 2 family dwelling in the 2020 NEC. Now, you can also have other surge protective devices downstream from that. You can have them in other panels, and as well as just the power strips and other things that we see.
Evaluating or put it in a dog hotel.
Somebody needs to be muted. Okay, the question was, do they work? Yes, they work. How should they be hooked up? Well, when you buy one of those, well, first off, you're going to see them in new construction. They're going to be built into the panel. They're going to come with it. Basically, you could have it that's a circuit breaker that you could also use as a circuit breaker for a branch circuit. They're typically 30 amps, so you could use it for your dryer breaker, something like that. Or it could be a device that you attach outside the panel and have wires that then connect to its own circuit breaker. Probably the most common defect that you're seeing with these things on these separate ones that aren't a circuit breaker is that they typically double tap them onto another breaker. They're not supposed to do that. The instructions always say, give them their own circuit breaker. But yes, they do work. Good question. Okay, interior piping. We want anything that is capable of becoming energized in that house to be bonded so that if it becomes energized, it completes a circuit so that the breaker trips. We don't want it to sit there with voltage on it, particularly if it's something like a gas pipe. It's an easy place to bond these different piping systems together is at a water heater, because they're all conveniently right there. We don't necessarily have to have the conductor that goes back to the service also connected here at the water heater. Earlier versions that we had of this drawing did have another wire coming off of this going back to the service, but your water piping is going to be bonded anyway by other regulations to the service. And here at the water heater, we've just got a convenient place to get the hot, cold, and gas together bonded.
Question.
So here's an example of using that illustration in a report. Yes. Question?
And I don't know what part of the country this is coming from. We are seeing new construction with an emergency, I guess, service disconnect at the meter, and the neutrals and grounds are still bonded or together at the main service panel.
Mm-hmm. Well, again, this is something that's a 2020 NEC requirement. It's a requirement that you have this emergency disconnect on the exterior of the building. One of the things that it can be is a meter disconnect, and it has to be a true meter disconnect, not a meter bypass, but a disconnect. If that is the case, that from that disconnect to the electrical service, there won't be a separate grounding, equipment grounding conductor. It'll still just be 3 conductors going there, the 2 hots and the neutral coming from that meter disconnect. So the meter disconnect is one means of having the emergency disconnect. Your service panel being on the exterior, having a disconnect is another way to do it. And a third way to do it is to have a shunt trip button. But I think that's what they're seeing. Now, I don't know who asked that question, but I would love it if you could send me a picture of that, because I've never seen it. I've only read about it. So I would love to see it. The one picture I have of it that IAEI used as an example of it wasn't really a meter disconnect. It was a meter bypass switch. So great question. So you could email us at CodeCheck, info@codecheck.com. We'd love to see a picture of that. All right. So back to the oldest question that we always raise of grounds and neutrals. Obviously, we bond everything together at the service. We've only got our 3 conductors coming in. Fairly recent change is that we also put these little boots over the terminals at the service conductors. This gets a little bit further into what the 2020 NEC says, and we don't want to go into that tonight, I think, as much. But I do want to look at the sub-panel picture, which this is probably something I would guess that you find sub-panels done incorrectly when you have a house with a sub-panel, probably what, 50% of the time or higher percentage, I would imagine. It's a very common defect. So this illustration is very useful for that, of explaining that you do not bond the neutral in the sub-panel, that the sub-panel requires the 4-wire feeder. And that here we have an example of one that is done correctly. This is a nice piece of workmanship. And here we have our equipment grounds, and here we have our neutral. And this also is one of those types of panels that has plug-on neutrals, so that the GFCIs don't need pigtail wires.
So Douglas,
Yeah.
just because we all get the realtor saying, well, that must be grandfathered, so it's okay. How far back do you have to go in the electric code to get to a point where it would have not been prohibited to bond the neutral and the grounds on a sub panel?
Well, they put the rule in 1918, but they didn't require grounding of AC systems until 1913. So if you have something built during World War I, you have bigger problems. So just an example of what can happen on this photograph is a sub-panel in an individual unit of a high-rise apartment building. And so what happens is that in each stacked apartment, there's this little compartment over here where the feeders rise up and they tap off a pair of them to each of these sub panels. And the tenants in this were reporting some electrical problems. And so an electrical contractor came along and he fixed it. What he did was he bonded the neutral in every panel in this entire apartment building. And then I got called in. What was happening at this point was that people were getting little shocks all the time. And that there would be somebody would touch their toaster and touch their stove at the same time and have a little bit of a shock and be startled by it. And what was happening was that they were low voltage enough that they weren't killing anybody, but enough voltage to startle people, which is actually referred to as a level of a voltage that you call startle current. And it was happening throughout the entire building. And it was because of this. It was because what happens is that not only is the current from the imbalanced load in this panel coming back through the neutral, it's also coming back through the equipment ground. It's the one thing Benjamin Franklin got wrong about electricity was when he said that it travels on the path of least resistance. It actually travels on all paths and divides up by the resistance of them. And so what happened here was really causing a lot of havoc. And just as a demonstration of it, here you can see I'm down there at their service equipment, and I got these various readings on the different conduits. This one had half of an amp on it, but everything throughout the building was carrying current. Things that should have been a zero reference were all carrying current. And as a result, people were getting these little startle shocks. The other thing I would expect to happen in a building like this is there would be a lot of magnetic fields as a result of these currents. You'd get, it would interfere with real clear audio reproduction and possibly even with other electronic equipment. So one of the illustrations we have also is showing the required spacing and placement of receptacles. And this illustration here is a sideways illustration of it that we created just for the illustration set. The way it appears in our book is like this, but we thought that it would be more useful for home inspectors to have it in a landscape orientation instead of a portrait orientation. So there are a few things that have been recent changes in the in these codes. One is that the requirement for wall receptacles does not apply to places where there will be a full height cabinet that takes up that entire wall. If those cabinets have countertops, then the rule does apply that we don't want to have anything further, any part of that wall further than 6 feet away from a receptacle outlet, which means if I go 6 feet away from that one, I've got to be within 6 feet of the next one. It gives us a 12-foot spacing, basically, something that's been in the code for 60 years or longer than 60 years. So we've had a few changes on recently on peninsulas and islands. We'll get to a couple of other pictures that show that in a bit more detail. But basically, when you are looking at a kitchen or any room that doesn't have the required number of receptacles, then this is a good illustration to support where you think they should be. And here's another illustration just showing that 6 foot, 12-foot rule. For islands and peninsulas, we have a problem when there's this countertop surface all the way across there, it's not as convenient as with a wall where you just plug you have the receptacle in a wall to serve that countertop. What happens here is we have two competing safety factors. One factor is that we don't want people to have to use extension cords, because if they use extension cords, they're going to be draped across the sink or the stove, or people are going to trip on them, etc. So we want to have receptacle outlets where appliances are going to be used. But if we have receptacle outlets on the side of a cabinet like this, what can happen is that you plug something into it. Say, imagine we have a crock pot or frying pan sitting up here on top, and a little kid walks by, they can grab that cord, pull that appliance down onto themselves, and have all kinds of bad things happen. So on the one hand, we want receptacles to serve this island. On the other hand, we are wanting not to have receptacles there. So for instance, in the 2017 code, which I believe all of the Mac ASHI, Nova ASHI people are operating under, that or an older one, you only need to have one receptacle for this island, regardless of how large it is. For each island countertop space, you only need one receptacle. Now, if the island was broken up and by having, say, a sink in the middle or a range in the middle, then the spaces on each side of it would each need their own receptacle outlet. But it's basically one receptacle outlet per island or peninsula countertop space. And if we go back and look at this peninsula here, in the 2017 code, the outlet on the wall over here would be the only one it would need. In the 2020 code, you have to have one at least 2 feet from the end of the peninsula. But in the 2017 code, the one on the wall was all that was necessary. So I mentioned there's two competing safety factors. So it sounds like the thing that was really dominant in the 2017 code was the safety factor about the danger to children from having these receptacles. Well, the 2020 code went the other way completely. So that what it says is, oh no, we need a receptacle outlet for the first 9 square feet of that countertop, and then another one for each subsequent 18 square feet or fraction thereof. So if my island was, say, 4 feet by 7 feet, and I have friends who have kitchens that have islands that big, that would be 28 square feet. So I'd need one for the first 9, one for the next 18. Oops, I'm over that by 1. Got to have a third one. Got to have at least 3 receptacle outlets. So that's what they did in the 2020 code. In the 2023 code, they're going to go back the other way. And this has gone back and forth, ever since they started paying attention to this, to countertop receptacle outlets in the 1990 code. So we're going to see for 11 code cycles in a row that they have to change what they did the time before. So this is where it's really interesting, I think, for you as home inspectors, because what really is important here is that you convey the safety concerns to your client. And there's a safety concern about not having enough receptacles. There's a safety concern about having them. And then there's also the solution if you have enough money. And the solution if you have enough money is the pop-up receptacles. But they do cost a couple $100s a piece. This is not the solution. You can't put it face up in that countertop, for pretty obvious reasons of what's going to happen when you spill something on it. lights in closets are something, again, that it was only fairly recently that this actually started to become regulated in the NEC. So we see a lot of older installations that that are pretty concerning. But basically, what happens is that we have several rules. First rule is that you cannot have any type of a bare, exposed, incandescent fixture in a closet. That if it's an incandescent fixture, it requires that it be completely enclosed so that you can't have something flammable that contacts the bulb. The next thing is that there's certain areas that you can't have light fixtures in your closet. The only time you're allowed to have them on the wall is if it's the wall over the doorway. And the reason for that is, suppose that you had a light fixture on the wall, and you turned it on and you're getting dressed and you take off the bathrobe and you hang it on the light fixture and you forget to turn off the light fixture. And a lot of our clothing, synthetic clothing especially, is highly flammable. So what happens is you've just put something flammable onto a source of ignition and waited for it to heat up. So what happens I can't remember exactly how many years it's been now, but it's only within about the last 30, 35 years, is first off, the light bulbs have to be completely enclosed. Next, they can only be on the wall over the door. And then that they can't be in the storage area where we're likely to have combustible materials. So we see this all the time on older houses. You see something like this, a keyless light fixture right in the storage area like that. So it's not a question of just covering it. You're not allowed to have it in that spot at all. So, and this is a fairly shallow closet, so they probably just should not have a light in there at all. That it is a fire hazard.
Question?
Yes.
Back to the kitchen a minute.
Sure.
Are the pop-up receptacles actually corded to allow the flexibility of the outlet, the movement?
Well, you've got a cylinder the same size as that that you saw up above on the top, down below below it inside the cabinet, and there's internal cords to that are rated for that moving up and down. And what happens with these two is when you close it down, it has a little flexible gasket that actually seals it so it's watertight. And that's part of the UL standard for testing them, is that they can't leak. As far as what wire you're bringing into it, that wire isn't going to keep moving around. It's going to be stationary on where it connects to that thing. I hope that answered the question.
I think it did. So all the moving wire is inside the unit. It's not
right
at all.
Right. And a lot of different people make these. First people to have made it were Thomas and Betts. It's a great idea. Only problem is they're expensive. Okay, there's two versions of this illustration in your illustration set if you've purchased these. This particular one is based on the 2020 code. In the 2017 code, there's two words that are taken out of this, and those words are receptacle outlets, because receptacle outlets are prohibited in this zone that is directly above the tub or shower and within 3 feet of it horizontally in the 2020 code, but they're not prohibited in the 2017 code. You could have an outlet in this part of the green area here. So we have two versions of this. Well, I would recommend that you use the other version of it unless you're on the 2020 NEC in your area. And even then, you probably aren't really seeing that many houses built to the 2020 NEC unless you're in Massachusetts or someplace that adopted it very early on, because typically if the plant that the code you have to conform to as a builder is the one that was in effect at the time that your permit application was accepted. So in the 2020 code has only had, well, I guess it's been in effect in Massachusetts for 2 years now. So they were the first. But the whole point of this illustration, though, is to show that we do need a receptacle within 3 feet of our sink. That we, because that's basically the cord you're going to get with your electric toothbrush or whatever, or your hairdryer, and that we don't want to have certain types of fixtures that are reachable from inside the tub or shower. And that would be a fixture that was on a pendant, like a chandelier, say, or a ceiling suspended paddle fan or a track light. So here is an example of using that illustration, and it's the older version of the illustration I see that says no pen, it doesn't say no receptacles. And it's calling out this pendant fixture that's hanging down less than 8 feet above the top rim of this tub. There's certain situations where you will need to have a lockout hasp on a breaker. The most common one would be if you have an electric water heater and there is no disconnect within sight, then back at the panel, you can have one of these lockout hasps that you can turn off the breaker, put a padlock on it, and then go to work on that electric water heater without worrying about someone turning the power back onto it while you're working on it. Electric baseboard heaters very often have these problems of receptacle outlets installed directly above them. And if you look at the listing instructions that come with electric baseboard heaters, they almost always will say that you cannot have these installed beneath an electrical outlet. They do make for some baseboard heaters, they make these add-on extensions where you could have a receptacle outlet that was in that space so that you're meeting your requirement for wall space receptacles, but that it would be built into it, but not on the same circuit. It can't be on the same circuit as the heater. So here's an example of what we're talking about. You see that cord is going to get fried sitting there. And here's also an example of something with a receptacle outlet built into it. We see these types of switches. This particular one's called an SSU switch. That's actually the model number for this brand. That are oftentimes used for the power supply to a furnace. And the reason that you might find this is that suppose you have a furnace that is on a 20 amp circuit. And for typically what you'll find for most furnaces that are rated less than 120,000 BTUs is that they're going to have a blower that is not drawing all that much current, and that the installation instructions will say, do not install on a circuit that has greater than 15 amp overload protection, but you've got it on a 20 amp circuit. So how do you fix that? What you do is you have an SSU switch with this fuse in it where you can put in the 15 amp fuse. Well, you can't just put in any 15 amp fuse. In any new fuse that you put in has to be a type S fuse. That is to say, it has to have an adapter and a set of threads that is unique to that adapter so that you can't put in an oversized fuse. So here's some examples of these. Here's an SSU switch. There it is with its fuse in it. But that one is actually the wrong kind of fuse. It should have been one of these, a type S fuse with a type S fuse adapter. Now you see that this is a 15 amp adapter and somebody trying to put a 20 amp fuse in it, and it won't fit. It's a different thread configuration so that it prevents it from ever seating and prevents overfusing. So shouldn't use an ordinary fuse, should always be a type S fuse. More appliance issues. For air conditioning condensers, oh wait, we didn't get to plumbing, did we? Oh my God. I'm really sorry. I've been timing this to end at 9:30 and I forgot plumbing altogether. Let's jump ahead. We're going to jump ahead a little bit here. Oh my goodness. I get carried away on this. I'm really sorry. I've just been babbling here. Okay, well, we're going to get to plumbing.
Well, Douglas, we're enjoying your presentation, but a couple of us have children to put to bed and things. So yeah, if you can.
Yeah, well, I promised Hollis we would end at 9:30. So, okay, so plumbing. And Jim assures me that you guys actually do have some ABS out there in older houses, and it's not all PVC. This is a nice example of the right way to support ABS plumbing. And here are some examples of the wrong way, where this can actually, the plumbing can actually move just with changes in temperature, and it can abrade itself on these types of hangers. And also these don't resist upward thrust of the pipe or hold it in a secure place. Here we see the wrong way and the right way to have a reduction in size in a drain pipe. In general, no drain pipe can be reduced in size as it goes further downstream. They can only get larger. But there is one situation, which is that you could have a 4x3 closet flange, and that would be allowed. You can't do it with one of these adapters. So here's the right way to do it. And a couple other little things about this that I like, that it's got the supports on the cast iron on the piping, not on the fittings. Should never be on the fittings. And that's a good shot of what a 4x3 adapter looks like. Here's the wrong way to do it. They've got the 4-inch pipe coming down. They haven't glued their joint very well. And they've got this adapter reducing it. And because they didn't support things, this pipe up here is broken. Another example of how not to connect two different materials. One of the most common problems I find with plumbing is using the wrong type of fittings, the wrong application for fittings. A sanitary tee is designed only for horizontal to vertical configurations. So you'll see sanitary tees on their back or on their side quite often. Here we've got one on its back, and it's also, we don't have enough room for that clean out to really be effective. So of these different fittings in our books, we listed a little chart of what each of these can be used for. But basically, when you go from vertical to horizontal, you're going from fast to slow. So you need something with greater sweep. When you're going horizontal to horizontal, you're going slow to slow. So you need something with greater sweep, although the IRC will allow these quarter bends for horizontal to horizontal down to 2-inch pipe. And when we're going from horizontal to vertical, we're going from slow to fast. That's the application for a sanitary T. So here we're seeing something that almost looked good, but we've got a sanitary T on its back again. Not the right way for that one in the middle there. Here's a sanitary T on its side. And here's a sanitary T that's upside down. If this was a vent arrangement, that actually would be correct, but it's not. It was a water arrangement. This is a very common problem, and it's almost impossible for you to see this after the wall is completed, but the problem here is that they've used a combo fitting instead of a sanitary T. So what happens is that the actual air inlet is below the level of the trap weir, and so this will still result in siphonage. It basically means that the vent isn't going to be working properly. So this is where they should have used a sanitary T, and they didn't. Here they're using what's called a low heel takeoff. That is okay for that application. They're using it instead of a sanitary T. Okay. Sewage ejector pumps. You probably do see these. And basically these illustrations are showing some of the details of what should be done on this and when they're required. That this is required when the actual fixture is below the sewer. When the fixture is below the upstream manhole, we need a backwater valve. But when it's actually below the sewer, then we need something to lift it to get gravity on our side to get it to drain. So the in this case, the what we're showing how the fixture below the sewer comes into this sump, goes through a backwater valve, and then a full wave valve to shut it off so that you can service it and clean it, and then enters into the plumbing system by coming into the top or the top half of this horizontal line. So what happens is that the sewage ejector pump is putting this under pressure here. And there's a little bit of a kick to it with each thrust of the pump. And that kinetic energy has to be taken out of the piping system before it goes horizontal. So that's why this has to come in at the top there. So there's a detail of it. Here's an example of one that's basically okay, although I would question whether ABS should be used as pressure piping in that application. Here we see one that's done the wrong way. That what's happening is that it's going from vertical to horizontal. Well, again, there's going to be a thrust on this for every thrust of that pump is going to turn into kinetic energy going back and forth horizontally here. So this whole thing is going to shake while that's operating, and it's going to keep shaking until it breaks. And when it breaks, all the stuff that's in your drains is going to come back down into here. This one's even worse. We've got a sort of an S trap here feeding into it, and then it's again moving in horizontally. Shouldn't be that way. This one's the right way. It's strange. It looks like an upside down trap in a way, but that is the right way to do it. Okay, speaking of traps, we always get lots of interesting things on that. First, the trap seal should only be 2 inches to 4 inches. A deeper trap is more prone to sludge. And then we hear all about the horrors of S-traps. And basically the problem with an S-trap is siphonage, that the trap seal protects the air we're breathing from the what's in our sewer system. So here we see a really old S-trap retrofitted probably on this plumbing system, but we also see a lot of them with really no excuse. This one's from a shower where they should have had a vent before that went down to that level. Here's one underneath the kitchen sink. Here's the basic idea. So this is there's a million ways to screw up the plumbing underneath a sink. You all know that. This is the drawing that shows basically what the right way should have been. And the whole idea is that before you get to the weir of that trap, we have to be introducing air. Otherwise, we're going to siphon this trap and suck the water out of it. And then it'll be just air in here all the way back to the inside of your house. So I love this picture because it has all the evidence is right there. There's the Drano, there's the plunger, but what's the problem? The problem is that this is so high up here that all of this is underwater all the time and then is prone to sludge. And they seem to think that the solution is to put more Drano down the drain. This happens a lot of times in houses where they've done a kitchen remodel, but they haven't opened up the wall to redo the plumbing, because older kitchen sinks before they had garbage disposers and so on would be very shallow sinks and would have a pretty high outlet for the trap. And what you need to do is lower that trap outlet down, which means taking off the wall when you've remodeled the kitchen. And if they haven't done that, then you're going to end up with this problem. Okay, I am very, very sorry that I took so long talking about electricity. I don't know why I like to talk about that so much, but I think I'm getting very short on time here. This is an example of.
Doug, you want to be sure to leave. You want to be sure to leave time to make your offer, and we got the drawing to do.
That's true. Yes.
Yeah.
There was one picture I wanted. Ooh, gosh, that was a good one. Wanted to get to for fireplaces, which was this one here. And this is this illustration of a direct vent gas fireplace, the kind that where you don't open the glass doors. It's just a solid glass pane there. We have a little notice on here at the end that says that the glass front can be dangerously hot and requires protective screening to avoid contact. Manufacturers offer retrofit kits for older systems that lack this safety feature. Skip, why do they offer those kits?
There was actually a big lawsuit. I met the attorney that was successful, and the glass on those direct vents can get up to almost 500 degrees. They literally had a 3-year-old child. He was the injured party in the class, who required skin grafts on both hands because and this is really disgusting, they had to peel him off of the glass. So very serious. I think it was a $500 million award. The manufacturers of most of the major brands had to go back almost 10 years and offer retrofit kits for free. So my suggestion is take these seriously. They're not toys. They're intended to be decorative, but the ones that don't have safety glass on it, or safety screens on it, I recommend that they, on all my inspections, that they contact the manufacturer to see if a retrofit kit is available for it, and to warn them about the burn hazard. It's not just little kids, it's pets as well. I mean, think of a dog sticking their nose onto it or something like that.
Right.
They also get installed improperly a lot. A buddy of mine, a colleague, Dale Febb, who's the best fireplace guy in the world, does a lot of forensic fire investigation stuff. He calls those, and I quote, a growth segment of his business, meaning they
Mhm.
burn down a lot of houses.